Always a pleasure to be here. I think this is my 7th GTC. It feels like we're really making some interesting progress in the world of real-time graphics. Our mission, I think I said this at the very first GTC I spoke at, is to make the holodeck happen. I'm sure a lot of you guys are probably Star Trek fans, and if you are, you know the Star Trek holodeck is a room that you walk into where everything is real, and of course, the graphics power needed to make that happen is remarkable. And there's a lot of hardware, there's a lot of pieces that seem sort of fantastical, but they're really coming together, and a big part of that is the GPU itself, and hardware ray tracing, which is something that we've dreamed about for a long time, is finally here. So when we first started OTOY as a company, and we've been doing this now for over 10 years, things were pretty primitive back then. If we were thinking about how to capture things from the real world, how to digitally render them and display them, the technology that we had at the time really wasn't very advanced, but the pieces were there for what would come later. So OTOY as a company is focused on 3 different parts of the graphics pipeline. Capture is one of them, rendering is another, and display and streaming is the third. This is a prototype capture system and a spinning mirror that is generating a true light field. And it's monochrome, but this was tests that were done by Tim Hawkins and Paul Dvevic at USC. They later came to work for OTOY, and Tim just won his 2nd Oscar for Lightstage. But this is showing a capture of a real person on Lightstage and displaying it on a spinning mirror. And of course, the goal is we want to be able to capture the world volumetrically on our phones. We want to be able to stream it from the cloud. We want to have this render with complete fidelity. So here we are 10 years later, and OTOY is focused on these 3 different vectors. On the rendering side, many of you are probably Octane users. Show of hands. If you're not Octane users, are you familiar with Octane? Okay. Well, if you're not familiar with Octane, this is what it renders. It renders the TV shows and the movies that you're probably familiar with. It's very fast. It's actually one of the very first GPU renders on the market. It is, to this day, I think one of the best and highest quality. It doesn't cut any corners. It gives you the laws of physics and light. And the quality and the ease of use for artists is truly unsurpassed. Now, we've also gone the other direction. We've been trying to bring this technology to video games, democratize rendering for everyone. And in order to do this, and I think certainly the GPU itself has been a big part of helping to bring technology and software like Octane to the masses, we've also partnered with companies like Unity. And Octane is now integrated in Unity. 6 million Unity developers can use it. We've also, on the capture side, tried to bring our high-end Lightstage technology for capture also to sort of prosumer devices. And most recently, we've partnered with Facebook on that endeavor. So on the capture side, I want to start by talking about what we started doing at the very high end. Lightstage is this giant rig that you see here. It has hundreds of lights, but you put something inside of it, and what you get out of that at the other end is something that is perfectly relightable. It's more than just color and depth. It has all the properties of whatever you put in there, including skin and surface reflectance, which is really, really important for digital doubles. And in fact, Lightstage has been used, for the most part, for films and television shows where digital doubles are a requirement. And it's also become cheaper. So now you have every single DC TV show that's on the air that uses Lightstage, of course, movies as well. But we've also started to think about how to get this technology into game engines. So we actually had Lightstage used for Paragon assets by Epic. And of course, we want to bring this technology to game developers. And Lightstage itself is really special. If you look at this render, it is a render. It's basically shader-free. There's no shaders in this model. It has all of the properties of the reflectance field of the skin that was captured in the Lightstage. And you just have to hook this up to the incoming light, which could be a panoramic camera on the phone, and you get perfect relightable holograms. And we've been improving this technology to get us very fine details, such as eyelashes and pores. That's why Lightstage is actually so valuable for films where you have this kind of fidelity as a requirement. And we've also been working very hard to shrink this down. So this is 2 lenses, 2 point grade cameras, generating a Lightstage scan that you can then feed into a game engine and relight. So this is ultimately the culmination of a lot of years of research and work to shrink something that was used by ILM and Weta and Digital Domain to something that we can start to embed in cheaper and cheaper cameras and phones and devices. And it can not just capture people, it's also very useful for capturing surface properties if you're doing real-world reconstruction. Lightstage is able to separate the color from shadows. Of course, it's also able to generate these very beautiful and high-quality normals and surface properties. And it can even be used to infer material properties of metal. So if you want to completely reconstruct something that has glass or windows, Oculus was showing a piece of technology that did something similar to this, but LightStage can be used to actually give you the index of refraction and the approximate roughness of specular materials and metals. Very valuable. So again, photogrammetry is one of the big things that we want to see LightStage used for. This was actually one of our Octane users for a contest that Oculus did, went out and did this photogrammetry work, had to manually paint the normals, but generated this beautiful scene in Octane. And we think we can simplify that process. And certainly AI for things like scattering vegetation and grass is going to be important. We were talking about that in a rendering session that we had this morning. And also, if you just capture the raw light coming in from a light field camera or light stage camera, you can get something that is pretty neat. You get something, you can already see in this scene here that you can see things like glass reflections, you can see around objects. A light field truly is something like a hologram, and a reflectance field is deeper than that. A reflectance field gives you all of the information a hologram would have, but also how you have to light that. So turning this into something practical, Facebook had been working with us for many years on various different projects, but they had seen some of the prototype work that we had done to shrink LightStage down and build light field and reflectance field cameras. So that led to them initially working with FLIR, and then finally last year they announced that Red would be making this amazing manifold camera. It's expensive, but you can rent it, and it'll be used in productions this year. And the part of the pipeline that OTOY is involved with is largely taking the data from the Red camera and feeding it into the cloud, feeding it into a collection of applications, some of which Facebook wanted to make sure we covered, such as Foundry Nuke and, of course, Adobe After Effects and Photoshop. But our plugins and our ecosystem connects all those different pieces together and ultimately streams the volumetric video that you edit and create to the Facebook newsfeed. And every year we've shown progress sort of in building out this ecosystem. It's interesting to sort of see programs like Nuke. If you guys are users of Nuke, you can bring in assets that are scanned in from the Facebook Red camera, and you can drop in any CG asset you want with Octane and blend those together. And that's obviously an interesting step for the prosumer market. On the consumer market, of course, you've got cameras on the backs of phones that can do depth reconstruction. And we've been trying to get that to be a little bit further along, but we're missing a couple of pieces. As soon as we get cameras, 2 cameras on the backs of phones that can do 120 hertz in stereo, and we can add a pretty cheap system of lights, we can actually improve the photogrammetry process on a phone with the technology I was showing before with LightStage, which will allow you to fill in those holes and fill in all these different pieces with much higher resolution details. So that's the capture side in a nutshell, and I'll connect back to where that all fits together for the holodeck in a little bit. On the render side, Octane has been really sort of the heart of OTOY's GPU efforts now for almost 10 years. It's hard to imagine, but Octane actually was released in 2009, the end of 2009, so it's going to be about 10 years that we've had a GPU render on the market. And in the early days, its ambitions were really focused on architecture and visualization, so images. In 2012, we started to focus a little bit on animations. By 2015 and 2016, Octane 3 was really far enough along that it was able to do full productions. And in fact, these all won Emmys. So, the opening of Westworld, The Crown, American Gods, all done in Octane for Cinema 4D. Ant-Man and the Wasp was also rendered in Octane and C4D. And it's really fascinating to see Marvel movies now done on GPUs. This was unheard of 5 years ago, much less 10 years ago. And very proud of this. This year, the opening of Doom Patrol was all rendered in Octane, same studio, Elastic, and they just do beautiful work. And the great thing about what Octane's able to do, and it's a game changer, I think, is that you really are able to produce content for television shows with 3 artists and a couple of GPUs and crank out these absolutely beautiful renders. There's not a lot of iterations. The quality is absolutely beautiful. And they're really, I think, and of course I'm a little biased, I don't think there's another renderer out there that's quite like Octane. I mean, it really is the laws of physics and light, and there's no shortcuts. You can certainly, make it render faster, but it ultimately gives you this ability to run a simulation, and that makes it really easy to be sort of a cinematographer and not worry about the different steps to render. There's no two-step process. Octane pretty much renders live what you see in the viewport. And I'm going to go over sort of the last release cycle. Last time I was here, in fact, since SIGGRAPH, we released Octane 4 at the end of last year. And that integrates Brigade, which was a technology that allows us to do 60 frames a second dynamic games inside of a path tracer. And we worked a lot on technologies for doing AI denoising and AI lighting. So this is Brigade. Before it was integrated in Octane, you can run bullet simulation of physics, all these things. This is running on a 680, so this was long before RTX was there. But with RTX, we now have the power to make something like Brigade run without any noise. And that's something that is truly exciting. I mean, we were imagining that if you had about 20 GPUs back in the day when we were working on this demo, you could maybe get Brigade to run noise-free at 1080. And we'd still have that sort of situation where we're plugging, for example, Octane or Brigade into Unity. There's still a little bit of noise. So that's one of the reasons why we developed an AI denoiser. And it's something that's built deeply into Octane. It's able to handle things like glass and specular reflections really well, so it has a deep understanding of the scene. And with this technology, we're able to actually render for just a second instead of a few minutes to get a noise-free render. And that's something that we, of course, want to apply to real time. So between the advancements in tensor cores and ray tracing hardware, we think that there's going to be a point where Octane and Brigade will be able to cover completely everything in the spectrum of real-time games. But there's still a little bit of ways to go. So there's other things that we're looking at this year that can maybe get us there quicker. The ecosystem that Octane is connected to is also pretty remarkable. There's 26 different applications that have Octane plugins. Starting in November, you can actually get a single annual subscription to Octane, and you get all of them. So it doesn't matter whether you're a Photoshop user or Unity user, Blender, in fact, Blender and Unity and Unreal will be free. You get all these different plugins, and you can actually exchange assets between them completely with preservation of materials and lighting. And that's very important for a tool like Unity, where you want to connect something like Unity to Cinema 4D or Max or Maya, bring in assets, have them rendered exactly as they were in the original tool. And while there are things that allow you to bring in maybe meshes, you have FBX, Alembic, the Orbex interchange format that we sort of built into the very structure of Octane allows us to take any sort of lighting and material information and preserve that as well. Later this year, we're going to be adding Material X support, USD, and MDL. So Orbex has a subset of other formats that are open source that it supports, including open shader language. But these assets are all able to be interchanged between all these 26 different tools. So that's Octane 4 was a lot of work. We spent a couple of years on it. Going forward, we're actually going to be releasing Octane 3 times a year. And the reason for that is because things like RTX and AI are advancing the state of the art so quickly that we have no choice but to roll out major upgrades and versions a couple of times a year to really keep up with some of the things that we can now do on ever-evolving hardware. So the end of last year, we released Octane 2018, only a couple of months after Octane 4. It is now the latest stable version, and we did a lot of awesome changes in that release, including being able to do very fast volumetrics and also procedural shapes, which is one of the big things that we felt was necessary for GPUs, because sending data over from the CPU host app to a GPU takes time. If you're able to calculate with open shader language a fractal or a procedural shape on the device, you're able to get much faster results, and that's why everything in here appears like it's real time. And that's something that CPU renderers were able to do because they would share the device memory with the host application, but GPU renderers have suffered this latency or this sort of chugging of data. So we wanted to eliminate that by having open shader language, dry procedural shapes, as well as textures. What we're working on next, and this is going to be out this week, the very first test release of Octane 2019. And we've also been working on some of these pieces for a very long time. So I'm going to show a quick little teaser of a project that's being done in Octane 2019.2, which is not out yet. This is done by Big Lazy Robot. What's awesome about this clip is that it's being done just on a few GPUs. It's using the AI denoiser. This scene renders about double the speed, even without the denoiser, on the ray tracing cores that are on the RTX cards, and it looks awesome. And this is the kind of workflow that Octane is designed to provide. It allows talented artists like JJ Palermo, who's at Big Lazy Robot, to basically generate these things in near real time. It takes seconds to render these frames instead of minutes, much less hours, like in the old days. So I'm going to go through the features that are being released this coming week with Octane 2019.1. There's a number of them. If you're an Octane user, you probably have looked at the different pieces in Octane that allow you to apply different denoisers. So there's an AI denoiser that's trained on reflections. There's an AI denoiser that's trained on cleaning up volumetrics. So we've updated the volumetric denoiser. And if you look at the images on the left, middle, and right, you'll see the original noisy image. The middle one is Octane 4, which, and Octane 2018, which had the old denoiser model. And on the right is the same compute workload, but a much cleaner denoised image. And that's roughly 3 times the speed to get to a denoised image. And that's pretty great. I mean, AI is truly magical. And volumetrics are one of the noisiest things in Octane, especially when you shine lights through them. So getting that kind of clean result is pretty great. We need to look at every single part of the rendering problem to get to 3x or 4x of speed. The other thing that we've been working on in Octane for a while is refactoring the material system. While we do intend to support MDL, and we have supported things like a Uber material, really underlying all of these different material types is a bunch of simple, primitive material types, basically metallic BRDFs, sheen, diffuse, specular. If you mix those together, you can basically generate any material, but the complexity of how you mix these things together and keeping these things physically accurate can create a lot of problems. It can actually be very challenging to make that work and still be physically accurate. So Octane's solved that problem in this version. So you can create multiple specular layers. You can do things like having rain falling down a glass surface and have it actually refract correctly. You can do specular roughness, which is something that wasn't really possible in Octane before, because there is no such thing as refractive roughness. Sorry, I meant refractive roughness, but you can have 2 specular layers. One can be rough underneath it. And Octane now renders everything physically correct, but with all of these nice artistic improvements. And that's something that we've been able to do without any speed hit whatsoever. We've also added thin wall materials. And you can also stack materials really easily now. So it's a lot like Photoshop layers. Previously in Octane, you had to use mixed materials, which is still there, but being able to stack materials is much nicer. And that allows you to also do much more artistically driven procedural textures and materials as well that are also physically correct. The other big change that we've added in Octane, and this is in consideration of the ray tracing hardware that's now in really most mainstream graphics cards, is displacement. Displacement used to be a trick that we would do in shader code to basically do surface perturbations. Now what we do is we generate triangular meshes so that we can run that through the RT cores, the ray tracing cores, get much faster speed. And what we've done along with that work is we've improved the displacement system significantly in Octane. So you're no longer limited, like the old system, to UV meshes. You can now do anything you want. You can also send OSL code into the displacement system. So you can do procedural displacement. That is a game changer, and it's beautiful. You can mix different procedural displacements together, and it's very memory efficient. So this is a huge improvement in Octane that's coming out this week. This is it in action. It's also very fast. Even without RTX, the displacement system is able to render displaced meshes much more quickly than the voxel approach that we had before. It's still in there if you want to use it, but this is going to be much faster on current generation and future generation hardware. The other thing that we've added is the ability to send open shader language, which is a scripting shader language that's an industry standard, into volumetrics. And before, you had to bake the color into volumetrics from Houdini or Turbulence FD. Now you can just completely do whatever you want inside of a volume. You can even generate clouds or volumes completely from scratch in open shader language. And this goes a long way, again, to reducing the amount of data that you have to send over the GPU. If you don't have to send a texture and you can just send a procedural 3D volume that's calculated in shader code, that's going to be much faster, especially for interactivity. We've also added NVIDIA's rounded edges shader system. And it is a big improvement over the very fast but not very accurate rounded edges system that we had in Octane 2018 and earlier. So that will be coming out shortly. And it's an awesome system. It allows you to do concave and convex rounded edges. You can also allow different objects to be collected in the rounded edges calculation. And we're ultimately going to move that into curvature maps and add trace sets to allow you to have even finer grain control over this. But it's very fast. We're also building a completely new rounded edges system in about a month just for RTX. And that'll also improve the speed significantly. The other big feature that we've gotten a lot of requests for is to have primitives inside of Octane itself. Normally, Octane make a mesh, you turn it into a light, it all works. But people want to have light primitives. We added a spotlight before. But these light primitives will also be sampled much faster in the coming months. And that will be something that also is easier for the various 26 different plugins to standardize across. We've also used open shader language for cameras for a while. It's allowed some of our customers and users like deadmau5 to do awesome projections in Octane and completely code anything they want. But the average user just wants to have lens distortions from Nuke, or being able to do a custom lens that's made from a procedural noise. And all these things can now work inside of Octane with the universal camera node. And it looks awesome. I was just testing this keloid clip that you guys saw earlier through it. And you can now create really complex lens aberrations and effects that are instantaneously rendered. It's really nice. The other AI-related piece of technology that we're introducing in this version of Octane is AI upsampling. So we've been using that ourselves offline to do very high-end renders that are 16K. For example, our SIGGRAPH video wall, we rendered it in 4K. AI upsampler last year saved our artists a ton of time, and now we're embedding this in Octane. So inside of the viewport, you can render at a quarter resolution. It's 4 times faster. And I'm actually switching back and forth here. You can really not tell which one's the AI upsample version and which one isn't, other than a little bit of jitter and noise. So this also will improve, but this is another 4x speed gain. And of course, you don't want to use it for postage stamp size renders, but for 1 megapixel or half a megapixel, it's pretty solid. Again, towards the faster release cycle, 2019.1 will be stable in April, and about 4 months later, we expect to have a stable release of 2019.2. One of the big features that users have asked for is random walk. So we have that working in the internal build of 2019, and it's very fast. In fact, volumetrics and subsurface scattering that are based on random walk are about 3 times faster than Octane's older subsurface scattering system. So it's a big win, and it's interactive. It's really nice. So it's still very early, but it's already looking very promising. We're also adding a completely new hair system as well, and that will allow you to have really nice spectral hair, which is important for these kinds of digital doubles that we want to target with Octane and still keep the spectrally correct workflow that we've been working on for all these many years. We're also going to be adding features that we announced last year for Spectron. The next one is going to be fluorescence. That'll make it into 2019.2. And later in the year, we're going to add polarization and diffraction. The big feature, though, one of the big features that is that we're very happy and proud of for 2019.2 is full RT core support, full ray tracing hardware support. Last year, we went on a limb and said, we think it'll be 6 times faster. It'll certainly be 8 times faster than the previous generation. And certainly in tests that we were doing with OTOY ray tracers, it was looking like that would be the case. But it took a lot of work and effort to finally get to the point where we'd have a sense as to how fast Octane would work on shipping hardware. And we started to get our very first results this month. We put out a public benchmark, which has been written about in on different blogs. And so people can test their ray tracing cores with a version of Octane that was just a benchmark. And it's 5 times faster when running AO kernels on the very same 2080. So that's basically about 10 times faster than a 1080, which is, that's an order of magnitude. That's insane to go from a 1080 to a 2080 and render anything 10 times faster. But here we are. So the real question was, how could we apply this to path trace graphics, which are not shadow rays? Well, to our shock and surprise, and of course, we're thrilled, we announced this today, and this build is actually out there now for users to start playing with. We're able to see about 6 to 7 times the speed with path tracing and direct lighting with multiple bounces on scenes that have a lot of complexity and heavy geometry like this one does. This is actually the splash screen to Octane 3. It was done by one of our users for, after you guys saw that scene earlier, but it has a ton. It has 400,000 different instance meshes. So that is something that RTX will speed up significantly. So we're seeing pretty much the maximum possible speed in this scene, and it's for a final render. It's incredible for me to be able to actually sit there and get this rendered back in 1/6 the time just by turning RTX on with no loss of quality or fidelity. It's incredible. That's not the only scene, of course, that's getting pretty fast speeds. We're seeing that with anything that has forests and trees and grass. But even, and this is something that we weren't sure about, we're seeing 3 times the speed with RTX on in path tracing in an interior scene. And these are notoriously noisier than outside, sunlit grass fields. So even so, we're seeing 3 times the speed on a 2080 Ti. That's incredible. It's not every interior scene, but there's enough now that we have about a dozen scenes that are showing really promising speed gains, that this is compelling. It's not a corner case. It's not a synthetic test. These are all real scenes. This is the benchmark that we put out a few weeks ago, thinking that this was the fastest possible speed we might see in path tracing. It's about 2.5 to 3 times faster. But there are actually many scenes that we've found since then that also are in the 2.5 speed up range. And this is all with path tracing, which is awesome. This was a promo video that we did of Octane, I think Octane 2. So these scenes were never designed for RTX, and they're seeing 2.5 to 3 times the speed up, which is phenomenal. This was a Transformers production scene. I showed this on stage at GTC 2013 with Jensen. We had 100 GPUs. Now it renders 2 times faster on any GPU, and that's pretty cool. That is pretty cool. That's a scene you guys were seeing before. You saw the AI upsampler making that render 4 times faster, but RTX will render it almost 2 times faster without any issue whatsoever. Now, the reason why these speeds are a little bit less is that the scenes are getting simpler. So the more complex a scene, the closer you get to that 6 to 7x, and the closer it is to something like a cube or a box with very simple shading, the lower the speed up will be. So we're now roughly where a scene like this, a shot like this with just one object in it without much else might get 1.3x. That's still a lot. I mean, that's still that's basically the leap without RTX from a 1080 to a 2080. So that's still nothing to sneeze at. And it comes for free, basically. We're seeing our old Octane bench scenes were done, frankly, in 2013, so they're very simple, but they still get about 1.3x. As we get to really simple scenes, it's just a light bulb on a little mesh. That's about 5 to 6%. So basically, the ray tracing cores aren't being used at all, and they're just sitting there idle. So that's why this scene won't get any speed up, nor will volumetrics, but everything else will. And most of these scenes just came right out of the box, and you guys are seeing a spectrum of speeds that are in the 2x to 3x range, but also, in many cases, in the 5x to even 6x range. So that's pretty exciting, and it's huge. I mean, time is money. So for us, being able to render things in half the time, or 1/6 the time, is incredible. Our users will thank us for it as well. We've also been building a tool chain to leverage a piece of tech that we felt was important, and that is being able to move some of our code that's been done in CUDA in the past to Vulkan and Metal. We have a lot of Mac users, and the Mac right now is sort of in a complicated place. You have to use an eGPU to connect your NVIDIA card to Octane on the Mac, and it's sort of a kludge, so we wanted to try to simplify that. So part of that work was to come up with a language that was basically GLSL compute. We write it once, and it can spit out different backends. It can do CUDA, it can do x86 code, it can do Vulkan and Metal. And so we started to write pieces of Octane that were that we felt were needed in this framework. You'll see why in a second, so that we could run it on all these different devices and still connect that to CUDA code. And we got as far as being able to take the very bare bones path tracer inside of Octane and run it on an iPad or an iPhone. It's pretty fast. It's actually, the iPhones actually have a faster GPU than the Intel integrated graphics, and even some AMD laptop GPUs, which is pretty fascinating. But this is awesome. So this is, we got working last night. This is with the very first version of Vulkan and Metal, basically the tone mapping and just the pieces needed for Octane to run on a MacBook, Intel integrated graphics. The rest of the shading is being done over Wi-Fi to a GPU. It could be anywhere on the cloud or on a network, but it's processing the tone mapping locally, and you have Octane or C40 running on a Mac locally, and this is basically headless rendering. So this is a huge, huge feature that we've been trying to get into Octane for a long time. It'll just automatically turn on, and you basically, if you're already using Octane over the network, this will allow you to have 0 GPUs on your host machine, so you can just connect to a, some sort of CUDA device out there. And if you need to do something very simple, like just info passes, you don't even need a CUDA device, but for anything more advanced than that, the shading will be done by an NVIDIA GPU somewhere on the network. So that's awesome. The other thing that we're working on is something called, it's basically a kernel that's designed for RTX. So you're seeing the spectrum of speeds that we're getting from 2x to 6x, but what if we could guarantee that the speed would always be 5 to 6x? What if we could guarantee that we would always have real-time speeds, but there would be a trade-off. And the trade-off is that we'd have to simplify the shading in the material pipeline behind the scenes. And that's what we're doing in this case. This is basically a test kernel that we're going to be shipping later this year. And it's actually sort of a revisitation of Brigade as we had imagined it. We had built in to Octane the ability for you to move objects around very quickly, but we never did anything about the shading. And Brigade had some fancy things in the shading pipeline that we never added in Octane. We are now. And in fact, this part of Brigade and Octane will actually be something that you could run on an iPhone or an iPad, and that's very important for AR and things you'll see shortly. But the simplified lighting kernel is able to run 4K 60, and it does use RTX, and RTX is actually pretty important because without that, we're not, we need to run at much higher resolutions using ray tracing, and this is what the results are. It looks absolutely noise-free, and you're running at 4K 60. You could also run at about 16K by 10K at about 30 hertz on 2 Quadro 6000s, which is important for volumetric and light field displays that we're working on, and this technology will be applied to that. We're also looking at bringing this technology, both Octane and Brigade, in tandem to game engines, not just Unity, but Unreal Engine. So this month, we'll be releasing our integration for Unreal Engine. We announced it at SIGGRAPH last year. We've been working with Epic to make that happen. And Octane and Unreal is awesome. We're very proud of the fact that it's able to convert pretty much any material that you can throw at it from any samples that Unreal has into Octane materials, vice versa. The node graph for Octane, anything that you bring in from the interchange system is embedded in Unreal, and you have the Unreal node system. It's one of our best integrations. I think it actually is probably tied with the C4D integration for the kinds of clever things we're able to do. Obviously, Octane, when you're running it as a path tracer for films, it's not quite real time in this case, but we are basically driving cinematic viewport from Unreal, and it's definitely going to allow Unreal to make movies. I mean, production ready movies right out of the box. But we are going to be applying some of the tricks that we were showing before with our real-time technology into the same framework as well. And that brings me to some of the challenges that we're talking about going back to the holodeck problem, right? If we want to render holographic content, I was mentioning before that there's a 16K display that we were working on that was actually that needed to be driven so that you'd have enough rays to generate a white light hologram. We've been working on ways of getting that to happen through AI, but also through just encoding the data that's spit out of the renderer as a holographic asset. And that technology has been something we've shown for a while now. You can basically take simple 6-sided cube and you can have a holographic texture on it or holographic volume. You can move through it. Truly, this is like the walls of the holodeck. And it doesn't give you everything, but it does look absolutely flawless. So we have this technology that we're sort of mixing now with RTX, Brigade, and other technologies to provide you with something that could drive a true holographic display panel. And this is something that we've also intended to mix with the Facebook pipeline and the Facebook camera as well. And the other part of the stack that we've been heavily invested in is how to get the GPUs we need to render holographic assets, because holographic renders are not like 4K or 8K. I mean, they're basically 1 trillion pixels per render, so maybe 100 times more work than rendering a regular 2K image or stereo. So one of the things that we had been doing is saturating a lot of the public GPU cloud power, just doing single holographic renders. Even some of our stereo cube map renders for Oculus would just saturate the public cloud. So we developed a system that's based on Ethereum. Last year we launched a token that allows you to use your GPUs, sign up to the network, and we'll take work that we normally would send to the public cloud and provide that to you. And you can actually make an Ethereum-backed token that is basically roughly $1 equivalent to what you would pay the public cloud to do. Now, there's a difference, which is that when you're sending your data to the decentralized network, the render network, it's not MPA certified. It's not Amazon or Azure or Google Compute, where you have the studio level of trust. But what we found when we did a sort of our initial signups is that about 70% of Octane users don't care. I mean, they're basically going to render farms where the security isn't great anyway. This is actually end-to-end encrypted, so it's a little bit better. And the other thing that we're going to do, we're going to be providing is we joined Mesa, and we are going to be providing a pathway for larger data centers that want to join the render network to get MPAA certified so that they could compete for those kinds of jobs. Ultimately, it's sort of a more long-term goal, but right now capacity is so scarce that we need the render network to really fulfill all of the ambitions we have, and even some of the customers. Like, we don't really advertise cloud rendering heavily because we're concerned we don't have enough capacity for that. So we actually sort of organically got to this point when we started doing cloud rendering on Amazon. I think it was about 4 years ago for Oculus, their VR contest, 18K stereo cube maps. That was where we really needed a lot more rendering power. And we have roughly about 10,000 users using our cloud service. But high-end jobs use 2,000 GPUs. That takes down, significant amounts of the public cloud. And we just need more GPUs by an order of magnitude or more. So we think we'll get there. Render in 1 week of signups had about 14,000 GPUs, all very high-end 1080 Ti's. So that gives us about 1.5 million Octane bench, which is more compute power than we've ever had on any of the public cloud providers combined for our service. So that's pretty cool. The service is in beta, and it should go live on the mainnet, which is not test tokens, by June. And so far, so good. So phase 4 is going to be much more focused on things you can build on top of this service, including being able to take our compute library, photogrammetry work, even AI jobs, and run them on there. Anything that's related to things that go through our ecosystem, capture, render, or stream, is a suitable candidate for render. And of course, Octane itself is it's almost like gasoline. It really does utilize all your GPUs. If you have 100 GPUs, a scene can render 100 times faster, so on and so forth. So it doesn't really waste any resources, and it's able to divide workloads really cleanly across any number of nodes and configurations. But it does favor heavy nodes, and that's cheaper and denser. And that's what a lot of nodes on the render network have, because a lot of these users were mining Ethereum before the bottom of that market sort of went out from under them. So there's a lot of available GPUs, and with RTX, anyone that has a ray tracing hardware GPU will be able to render even more, which is pretty cool. So on the streaming side, I might need to reset this presentation. I think it's, here we go, let's try this. So on the streaming side, let's say we render a holographic asset. Render's done its job, it's there. It could be stored in an S3 bucket on Amazon, or we have a decentralized equivalent of Amazon S3, which is called Saya Token. We partner with them, they're another blockchain system. But the holographic assets are there, and we can stream them. And this is showing live streaming to an iPhone. It was actually done a couple of years back. And that means that the data doesn't actually have to all be downloaded to the device. So all these giant terapixels of renders that we're doing, they could be stored on the cloud, and they can be sent down. They can be mixed with VR, and I think this is really important because everything that people are trying to do with streaming, VR, and AR ultimately needs to be in world space. And we also have a great partner with Facebook. They're letting us really sort of kick the tires and experiment with all these different parts of their pipeline and platform, not just VR and Oculus, but also the news feed and 3D video. And that's also led Samsung and others to allow the streams that we're building, volumetric and holographic streams, to be ingested into their ecosystem. And we've brought on studio partners, Disney and HBO, are investors in OTOY, and we've helped them set up essentially volumetric websites and volumetric content on Oculus and other platforms. Although I think AR is going to be an important consideration going forward. So this is also showing what we were doing for Warner Brothers and other partners. We are also, in this case, launching from Samsung Internet. So we're very much in favor of an open metaverse, omniverse, however you want to call it. That's why USD, Material X, all these things are, and MDL, OSL, these are all really fundamental. We want data to be free. It shouldn't be in a closed format that locks your IP and property in something that you can't get back later. So all of this, before we talk about holographic displays, augmented reality is a big deal. And not just, obviously, the glasses that Microsoft and Magic Leap are working on, and others, but phones are a really, really, really huge market. And it hasn't really been cracked, I think, perfectly, but there's just a lot of phones that are out there. So of course, if we look at the entire ecosystem we're trying to build here, phone-based AR is something that is a big deal for us. So our light fill streams, again on the phone, this is an object that was scanned on a light stage, rendered on the cloud, now streaming back into the phone. On a Tango, which is the first phone that we could really have markerless, you can see it has no, it's an object floating in the air, so that's great. And with the pieces we built on iOS, remember that we have Octane's path tracer running on iOS, we can take scenes that are essentially flattened down for the brigade kernel I was showing you earlier, and what you guys were seeing running on that desktop GPU at 16K by 10 is able to run on an iPad Pro at 50 frames a second. And it looks absolutely awesome. So this allows us to solve one part of the AR problem, which is we want to be able to take huge assets, render them, load them locally. These are not light fields, by the way. These are full-on assets that are rendered locally. You can mix them with light fields, but now we have the option of doing both. And we can take assets out of that environment, drop them into the real world. All's good, it's working, we have clipping, sort of working here. Obviously with marker-based tracking, things can get even more precise, but the interesting piece here is the relighting. So if we are sending down an asset, whether it's a light field or whether it's rendering locally, we need to be able to light that asset and make it feel like it's part of the scene, and that is something that can be extremely challenging. So this is some of the earlier tests that we were doing, and this is what we were able to show last year at SIGGRAPH, but a lot of people haven't really seen this. But that is basically rendering live on the phone. It's picking up the light from our SIGGRAPH display wall, and I'm moving this character and object around. But it looks perfectly rendered in the scene. So, the future for us of applications is not just on the desktop, not just the legacy workflows that you have now, but things that are really designed for virtual set production. That's why Unreal is important. There's a lot of people that use iPads for movie productions, and they want this technology. So whether this connects to Octane in the cloud or on the LAN, or it's running locally, or it's mixed with light fields, this system just works. And we've been working on getting more and more of Octane to basically export to AR or holographic devices of any kind. Doesn't matter whether it's AR, VR, or potentially a future holographic display panel. It just works. And from the perspective of how this content could be consumed, I mean, the things that are rendered in Octane today that aren't in AR, actually, they blow up virally. This video from one of our users got 10 million views. It's just taking the Unity Atom model and rendering in Octane and C4D. But we can now do that on the phone live. And this kind of technology is something that we want to make available on iPhones everywhere. That also doesn't mean we can't use a bunch of GPUs. We can use 10 GPUs on the cloud, for example, to do the lighting or the GI for this. And that's also one of the reasons why even having a MacBook work headlessly with just the pieces you need to render locally for the display on the local device are so important. And we have content that are that I think will be really a good fit for things like Unity and Unreal. I mean, that's one of the reasons why we've been working on those integrations for a while. Obviously, Unity is used for a lot of AR content today. So, I have about 5 minutes, and I'm going to go through the next 4 decades, 1 minute. So, the 2020s, why we're doing all of this. Going back to the holodeck, the holodeck is truly, when you think about it, it's a truly magical experience. I mean, there really is no friction, right? There's no device. There's no glasses, there's no phone. You just go into a room and it's magically, you're teleported somewhere else. And when you think about it, it's not just for entertainment. I mean, you could have, schools, you can have meetings. I mean, all the things that are promised by VR and AR could be really transformed if you could build a true holodeck. So to that end, I was waiting for the display panels to come to market. I thought maybe 10 years from now, but as it turned out, there's a company that is building them, and they're doing a damn good job of that, and that company's name is Lightfield Lab. They're building these 4,000 dpi display panels. Right now, it's a 6x4-inch panel, but you can tile them together. And these panels aren't just for color. They can also emit ultrasonic, so you can touch them. And it's really hard to describe how good these look until you see them, and you can actually display and project a hologram on them. But the shipping product will be 2 feet by 2 feet, and like the Samsung LED video wall, you'll be able to chain this together and build things like concerts. Sides of buildings can be rendered in these things. And of course, the larger the display surface, the bigger and deeper the hologram can go. So tabletop, I think, will be absolutely a must. I mean, I think all displays by the middle of next decade will be probably holographic, because it's not more expensive, it just needs to be manufactured in high volume. And yes, you could build a holodeck, it probably would cost $15 million, but it could be done. You can curve these panels. They could be bridged together on floor and ceiling. It actually works. So in order to test the content pipeline for this before the display was built, we started with eye tracking. And this was rendering a light field based on where my left eye was being tracked. And that was a very, very, very early way of us to sort of see how this display might work. Last year at SIGGRAPH, we were showing this at our booth where we had shutter glasses and eye tracking, again, being able to display just 2 views, but it looked pretty nice. And what's interesting is on the actual holographic display panel, this very scene, I've seen it, there's no eye tracking, there's no shutter glasses, it just looks real. Like that door, that coat hanger is above the surface of the holographic display, and you can just touch it. It's incredible. You can put a magnifying glass through it or ground glass through it. It's truly a white light hologram, and it's absolutely amazing. So, there's only 1 or 2 of these displays currently built at Lightfield Lab in Santa Clara, but if you can make an appointment and want to see it, I highly recommend it. So, the display is 6 by 4 inches today, but again, you can chain them together to any size, and the more that you chain together, the larger the holographic surface is, the depth increases. I've seen them myself. It's more than retina resolution. There's something quite remarkable about seeing a true light field where your eyes converge correctly. This is something I've never seen in any device. And that's one of the reasons why we're so obsessed with getting everything to work right holographically, why we need to render all this amount of data, why we need to do all this work, why we need RTX, why we need denoising. None of this will work without it. And without that, you will not get to the Star Trek holodeck. I have about a minute and a half, so let's look at a decade from here. I think that holographic display panels will become a commodity, just like 4K is now a commodity. It used to be $50,000 to get a 4K panel, now it's $300. 8K will be the same, holographic displays will be the same as well. You're definitely gonna see this inside of autonomous vehicles and cars. If you're gonna be sitting in a car for 20 minutes doing nothing, you're probably gonna be in a bubble filled with holographic display panels. Maybe even your SpaceX rocket or Elon's Mars colonies can have rooms that are basically filled with these panels, especially if they're very cheap. And I think at that point, you'll also be able to afford a room-sized holodeck. You may not need garages as much, but it won't be something that'll be more expensive, let's say, than a fancy home theater. In the 2040s, I think holographic displays will be like wallpaper. And when you think about that and take it to its logical conclusion, buildings will be covered with holographic displays. So you'll be able to hide buildings. You'll be able to make buildings into anything that you want. And cities will change. At least they'll look different. You'll certainly be able to apply this probably at that point to clothing, to masks, to all sorts of things like that that are truly going to be wild. And yeah, I think that when you see the surface of the Earth covered in holographic displays, when you see your room, your house, we can't think about how the world works without internet, electricity, and light, but truly, I think there's going to be some sort of demarcation point where everything after the world becomes holographic is going to look and feel very different. And there's a lot of other things that are happening, of course, in parallel to that, but I think all of that is part of the vision that we have for a beautiful and an open ecosystem, a metaverse, so to speak. But I think that part of that is building the pieces decades in advance to make that really happen in the way that we want. So that's my presentation. I think I came in right in time. I don't know if we have time for questions. Thank you.